This conference will now be recorded.
Okay, students, good morning to you all. In this today's class, we are going to discuss about inductance of a conductor due to internal flux and external flux. So already we know that there are three parameters are involved in vital role in the transmission system for maintaining the performance. That is the resistance, inductance, capacitance. So already we derived how we can find the resistance of a transmission line, how we can find the data inductance of a transmission line. Now we are going to derive the inductance. It is totally different based on the how conductors are facing. Suppose we have different construction of conductors. Some conductors are single phase, some conductors are two phase. So based on that, we are going to calculate that inductance. So mainly, that if you want to find the inductance of a conductor, we should know that what is the internal flux linkage will be happening, what is the outer, that is surface, external flux linkage will be happening. So if you know these two parameters, then you can find that the total flux linkage, that is inductance of a conductor. Now we are going to derive the inductance of a conductor due to internal flux and external flux, and the both we combined, then we will find them a total inductance of a conductor. Now we will go for. See here, I will show you that if you consider a conductor like this, so this is the conductor. I hope you are seeing the paint. Suppose this is the ACSR conductor. This is aluminum conductor steel reinforcement. Here the internal part is the central core is a steel, and outer conductors are aluminum. And the main purpose of this steel reinforced steel material is for the mechanical purpose. And when the current is flowing through the conductor, the flux will be differ when compared to the internal as well as outer external flux. Now we are going to derive that what is the internal flux will be happening and what is the external flux will be happening, and based on that we can find the total inductance of a conductor by knowing the internal flux as well as the external flux. Now already we know that the inductance of a conductor should be depends on that the flux linkage of divided by current. So already we seen in one video the inductance. What is the purpose of inductor means it will limit the flow of current, and the inductance should be depends on that at what amount of current the flux linkages will be happening in the conductor. So that is given by the L. Now here we are going to derive this equation. L is equals to psi divided by I. And in this derivation we are using different parameters. That parameters are B, that is maximum flux density, H, magnetic field intensity, and nu permeability, and psi. So these are the four parameters we are using in the derivation of inductance. Now we'll go for one by one. See here, I'm like consider a conductor like this. And this is the outer view of conductor. It should be shown like this. And when the current I is flowing through the conductor, and here I am considering it, this is the let's consider, let us example ACSR. So this part is a steel reinforcement, and outer of this core is aluminum conductors. Now we have to derive that flux due to this internally and externally. So this will be shown here, and this part is entirely belongs to the steel. This part is entirely steel. From center of the conductor to the where the steel material is occupied the space, and up to now the distance between the center to here I've denoted as x, and from center to outer surface I'm denoting as the r. So here x is an inner radius and r is the outer radius. It means that from origin to where the steel conductor is located up to now the radius is denoted by x, and from origin to the center point to the outer surface is denoted by r. Now when the current is flow through the conductor, the flux will be generated from the center. So they should be start from center to, and it is elongated to the outer surface. Now I am considering one flux linkage. It is internally, that is dotted lines indicated here. Now the distance between this center point to, so the steel material to this flux linkage denoted by dx, and I'm considering a small part. That part is denoted by the ds, and this derivation is belongs to it is obtained by using the two laws. One is Ampere's law, and second one is Maxwell's law. What is mean by Ampere's law? What is the statement of Ampere's law? Anybody can say that? What is the statement of Ampere's law?
I by J, sir.
I'm asking a statement. So where
The
where
ratio of,
Ampere's law? What? Tell me.
it is the ratio of current per J, J, sir. Square per meters, ampere per meters
Suresh, you are saying
units.
formula. I'm asking statement. Where Ampere's law will be applicable? Right. At least by using Ampere's law, what we can find? Anybody? By using Ampere's law, what is the use of Ampere's law? Already you guys are studying in the EMF, right? What is the use of Ampere's law and Maxwell's law? No, right? I will tell you that. So when Ampere's law will be applicable means when the current is flowing through the closed path, then the magnetomotive force will be generated. That is called as intensity. So the closed integral of magnetic field intensity, it is equals to the current. It means that when the current is flowing through the any closed path, there be a presence of magnetic field intensity, and it is given by the Ampere's law. So let me see that what is the use of Ampere's law, how we can use in this derivation. So this is the initial consideration. So I'm considering the conductor, and here from inner to the up to one material I'm taking as a inner radius x, outer radius r. Due to the current, flux will be generating here. I'm taking one flux linkage, that is dot indicated by dotted lines, and I'm taking that one portion of the flux linkage, that is denoted by ds. Now the magnetic field will be established due to the current. So this is the initial consideration. Now we go for a derivation of inductance by using these two laws, that is Ampere's law and Maxwell's equation. Now see here the first sentence. The MMF in amperes turns around any closed path is equal to the current in amperes enclosed by the path. It means that when a current is flowing through the any closed path, there be a generation of magnetic field intensity with respect to the surface area. So this is a equation represents the Ampere's law. So here this symbol is indicates that it is a closed loop. the closed integration of H ds is equals to I, and here H is the magnetic field intensity, and its units is ampere per meter. So just keep remember the all units. So I will ask units also in a slip test, right? Now let the magnetic field intensity at a point X. So why? Because our intention is we are calculating the internal flux, right? So we are always concentrating on this X point. So we are always keep remembering of the X point. So we have to derive the equation with respect to the X point. That's why see here let the magnetic field intensity at a point H. So at point X, what is the magnetic field intensity is generating due to the flow of current, and it is generated by the Hx. This is the constant at all points as a field is symmetrical. Why? Because when it is symmetrical means when the constant current is flowing through the conductor, the symmetrical flux will be generated. So that's why I'm considering here Hx is a constant. Now, the integration of ds around the closed circular path is 2 pi x. Now, how it came is, see here, I'm taking the term, what is the area, that is circumference of this flux linkage. So, do you know that so this is in the circular path, and the circumference formula is 2 pi r. But r is the radius, right? So, here I'm considering that internal radius x. So, that's why its equation is integration of, that is closed loop integration ds is equals to 2 pi x. So this is the circular path, that is circumference of the inner circle, and it is equation 2. Now if you compare equation 1 and 2, there is a you can substitute 2 in equation 1. So where you can substitute means instead of integration of ds, so here this h is constant already we said, so it comes here, and integration of dx can be written as 2 pi x. So you will get hx into 2 pi x equals to I. So from this equation we can append the hx. So this is the final derivation. See, from equation 1, if you substitute instead of integral ds is equals to 2 pi x, from this equation you can append that hx is equals to ix divided by 2 pi x. So I already said that in the entire derivation we are going to derive the we are going to use the 4 parameters. One is magnetic field intensity, magnetic field density, and flux linkage, and L. So these are the step by step we are going to derive that. First one is magnetic field intensity, it is already over. Hx is equals to Ix divided by 2 pi x. It means that when the current is flow through due to the current, the magnetic field intensity will be generated in the circumference of the area. So that is the equation represented here. So let consider it is the equation 3. Now the first one is over. Now we have to find the Bx, that is magnetic field density. Let me see how we can calculate that. So until now, are you clear about this? Students, are you clear about until now? Up to Hx derivation, that is equation 3.
Yes, sir. Clear, sir.
Right. What about others? Right. So I don't want to waste my time. I'm going to continue. Now see here, as the current density is uniform at the both inside and outside. So up to now we derived the Hx equation, that is magnetic field intensity. Now we have to find the density of the current density of the conductor. So you know the relation, right? That is density represents that capacity. Suppose let me take the one vessel, based on the capacity, then we can fill the water. So it represents the density of the material, that the vessel, right? So similarly, based on the density of a conductor, it can allow the current through it. Now this equation where we can apply means I will tell you that. So this is the equation, right? Now so here the current the current through the circle, that is given by the pi x square and pi r square. So that density should be depends on the area of the circuit. So the area of the vessel, right? At the same time, so this is the area of the conductor. Pi x square is the area of the internal part of the conductor, and pi r square is the area of the outer conductor. Now here inner part, there is a flow of current is denoted by Ix, and its area is the current of flowing the area is pi x square. And similarly, the outer current is denoted by capital I, and the total radius of the outer surface is pi r square. If you apply the ratio between these two, ix by I and pi x square by pi r square, so pi get cancelled. Ix can be written as x square by r square into I. So this is the fourth equation we obtained here. So this equation represents that what is the current flow through the area of the circle. If the area circle will be increased, the current will be also increases, right? So based on the capacity, we can fill the more water. The same time, if the area will be increased, area of the circle will be increased, the current density also increases. So that is the relation we are obtaining here. That is Ix is equals to x square divided by r square. So Ix is the current at the point of x. So we are always just remembering that we are calculating the internal field that is belongs to the point x. That's why we are always remembering that we have to, there is all parameters in terms of x. Why? Because we are taking the x point for finding the internal flux. So Ix is equals to x square divided by r square into I. So x square is the internal radius and r is the outer radius and I is the outer current flowing through the conductor. Now if you see this, the substitute equation 4 in equation 3. Already we derive the equation hx. The hx is equals to ix divided by 2 pi r square. Ix is equals to 2 pi x. So this is the equation 3 we obtained previously. See. So this is the equation. X is equals to ix divided by 2 pi x. Now we know the value of Ix. If you substitute equation 4 in equation 3, then you will get like this. So Hx is equals to 1 by 2 pi x. So instead of Ix, I am substituting this one. X square divided by r square into I. So 1x, x will cancel. So finally we will get x divided by 2 pi r square into I, ampere turn meter. So just keep remembering that. I'm always repeating that you have to remember the all units for the components for magnetic field intensity, magnetic field density. So what is the units of magnetic field density? That is for B.
Weber per meter square, sir.
There is another unit there,
Sir?
Tesla.
except
Tesla,
right. So we can use two units,
Tesla,
either Weber per meter square or Tesla, right? Now we found that final equation of Hx. Now by using Hx, we have to calculate that B. So already you know that the relation between that B and H. What is the relation? B is equals to mu H. Right. So this is the relation between that magnetic field density and magnetic field intensity. Already we know the value of Hx. So X is a point where we are calculating the internal flux. So just remembering that. Now we already found that H value, and nu can be written as nu naught into R, nu naught into nu R, and we can calculate the B. Now let me see how we can calculate the magnetic field density by using this equation. So it is represented in equation 5. So until now, five equations are over. Now let me go for the next slide. Right. So this is the flux density at the point X. So this at this point we have to calculate the internal flux. So they already said the relation between magnetic field density and intensity is Bx is equal. So this is the point of equals to nu into Hx. So now substitute 50 equation from 6 in equation 6. So already we have the Hx value, right? So substitute here, then you will get Bx is equals to nu h divided by 2 pi r square into I. So this is the units of magnetic field density. One is Weber per meter square or Tesla. So now two parameters is over. One is intensity and density is over. Now we have to find that flux linkages. Let me go on next slide.
Sir?
So students, until now you had any doubts?
Sir? సార్ మనకు ఫ్లక్స్ డెన్సిటీ యూనిట్స్ వెబర్ పర్ మీటర్ స్క్వేర్ టెస్లా కదా సార్.
అవును.
కానీ ఇక్కడ మనము వెబర్ పర్ మీటర్ స్క్వేర్ అనేది 5/A వచ్చినప్పుడే కదా సార్ వెబర్ పర్ మీటర్ స్క్వేర్ అని చెప్పేది. మనం ఇక్కడ 5 లేదు కదా సార్ ఫ్లక్స్ అది ఏరియా.
ఫ్లక్స్ ఏరియా అంటే ఇక్కడ కరెంట్ ఫ్లక్స్ ఏరియా మనం ఎక్స్ డినోట్ చేసాం కదా, ఎక్స్ పాయింట్ దగ్గర డినోట్ చేసాం కదా, ఎక్స్ అనేది 2 pi. సో ఈ డెరివేషన్ అంతా మనము ఏరియా తో సర్కంఫరెన్స్ ఏరియా నుంచి కన్సిడర్ చేసుకున్నాం, డెరివ్ చేసాం ఇది.
అవునవును సార్.
వెబర్ పర్ మీటర్ స్క్వేర్ చూసుకున్నాం అంటే బి ఈజ్ యాక్చువల్ గా బి ఈజ్ ఈక్వల్స్ టు ఫ్లక్స్ లింకేజ్ డివైడ్ బై మీటర్ స్క్వేర్. సో ఇక్కడ
yes, sir.
2 ఆర్ స్క్వేర్ ఉందంటే ఆ రేడియస్ అంటే మీటరే కదా.
మీటర్ సార్.
సో ఆ మీటర్ స్క్వేర్ వచ్చింది. తర్వాత Ix అంటే when the current is flowing through the conductor, the outer surface flux will be generated. So that is the numerator reverse here. That's why Weber per meter square. So ఈ derivation అంతా మనము ఏరియా సర్కంఫరెన్స్ డ్యూ టు ద కరెంట్ ఫ్లోయింగ్ దాని నుంచి డెరైవ్ చేసాం. ఓకేనా?
ఓకే సార్.
Right. Now, so we have the two parameters. One is Hx and Bx. Now we have to find out what is the flux linkages. That is the change in flux in the area. Now, for the element having the thickness, and so thickness also one of the parameter will generate flux. So already you know that. So based on the thickness, where you can use the thickness. So there is any relation between thickness and that is a flux or EMF, whatever it may be. So let me take an example. In transformer, we have EMF is equal to 4.44. That is, voltage should be induced to EMF should be directly proportional to number of turns. So in a synchronous machine, we are taking that instead of number of turns, we can take the thickness. It means that the thickness is act as a one of the parameter to generate the flux as well as induced EMF. So that's why here thickness is one of the element I'm considering, that is dx here, and the flux will be product of bx and cross sectional area of the element normal to the flux lines. So here the flux change in flux is can be written as maximum the flux density at point x into length into dx. So here length is nothing but a 1 meter. So we have to take that 1 meter. There is a axial length of a conductor is 1 meter. So this is a constant parameter here. Now d pi can be written as x into L into dx. I am substituting instead of L 1 meter. Now from this equation, so already we have the bx value. So substitute bx value in this equation, then you will get d pi is equals to mu x divided by 2 pi r square into I. So this whole term is belongs to the bx value into 1. This is the axial length 1 meter and this is the thickness dx. So why? Because the maximum the flux density depends on that what is the thickness, and based on thickness how the flux will be generated. So this is the given by the maximum flux density from the relation we obtained here. So finally d pi is equals to, so here in this equation, so mu x divided by 2 pi r square. So finally I can write mu I x divided by 2 pi r square into dx. So this is the equation 8. Now from this equation 8, how we can find the flux linkage? Let me see that. Right. So this flux links with current Ix. Hence, flux linkage per meter is length of the conductor is given by d psi equals to x square by r square into d pi. So this is the flux linkage formula. So here x square is the internal radius and r square is the outer radius. So d pi by dx, d pi by d psi by d pi equals to outer, that is the inner radius square is equal divided by outer radius square. So these are the equations you studied in the EMF equation. So దీని గురించి మీకు చెప్పాలంటే it will take more time. So that's why I'm taking as a equation directly here. So the flux linkage equation is equals to the d psi is equals to x square divided by r square into d pi. So this is the equation of flux linkages. And substitute equation, that is a previous equation, that is d pi can be substituted here. Let me see what will come. So d psi is equals to x square divided by r square into, so this entire term is equals to the d pi. Now from this equation d psi is equals to mu into I into x cubed divided by 2 pi r power 4 dx. So this is the flux linkage in the inner area of the conductor. Now represent equation, it is 9. Now so so this is the change in flux, that is flux link with respect to the current. Now what we have to do means, so when the flux is generated at the center of the point, that center of the conductor, the flux should traverse from center to the outer surface, right? So that we have to find. So what is the flux? So I'm taking the conductor here. Sorry. So I'm taking the conductor here, and this is the center point of the conductor. When the current is flow through that, the flux will be generated. Now this flux, how much of flux will be travels from center, that is a center point to the outer surface. So now only we can calculate that what is the internal flux will be generating in the inside the conductor, not outer surface. So that's why we are going to derive here. So let me take that the flux linkage will be changes from 0 to R. So why? Because the radius from the origin to outer surface is R, right? So we have to find that what is the flux linkage will be changes from 0 to R. So that is the given by the internal. So up to outer surface, up to this point, the entire part will be internal only. So we have to calculate this internal part, and in the ratio, in the ranges between 0 to outer surface, the outer surface is given by R. So this is the equation of flux internally happening here. Now this flux will be changed. It will start from the 0 to R. That is the R is the radius from the origin to outer surface equals to d into d pi. So instead of d psi, I'm substituting here. Already we obtained in previously. So previous slide lo manaku d psi ochindi. So d psi ni ఇక్కడ substitute చేస్తే, now in this equation, the entire part is constant except x cubed. Why? Because we are differentiating with respect to the dx, right? So integrating with respect to dx. So x is a variable, remaining all terms are constant. So we are taken out from the integration. So we have to integrate only x cubed. The integration of x cubed. So already you know that integration of x power n into dx is equals to x power n plus 1 divided by n plus 1. So that is the formula for integration. Now if you integrate x cubed with respect to ds, you will get x power 4 by 4, and upper limit is r and lower limit is 0. If you substitute r here, r power 4 by 4 minus 0. Now r power 4 will get cancelled, and finally you will get internal flux linkage is equals to nu I divided by 8 pi. So already what is our intention? We have the final equation is in terms of L equals to pi divided by I. So we have to find the inductance due to the internal flux, right? So how we can calculate this L means by knowing this the psi internal flux linkage, then only we can find that what is the inductance of a conductor due to the internal flux. Now the internal flux linkage is equals to nu I divided by 8 pi, and its units is Weber ton per meter, right? So H is equals to H units is ampere per meter, density is Weber per meter square, and flux linkage is Weber ton per meter. So keep remember these three units. One is field intensity, flux density, and flux linkage. Now from this equation 10, we finally derive the what is the inductance due to the internal flux. So from this equation, that is pi psi internal internal flux linkage is equal to nu I divided by 8 pi. Now from this equation, we have to find the inductance value. So instead of already you know that nu can be written as nu naught into nu r. So this is the equation of a nu, and here nu naught represents the permeability of a free space, and its value is 4 pi into 10 power 7 Henry per meter, and nu r is a 1 per non-magnetic material. So these two are constant values, constant parameters. Now instead of nu, I can substitute here nu naught into nu r into I divided by 8 pi. So instead of nu naught, I can substitute 4 pi into 10 power minus 7 into 1 into I divided by 8 pi. So 4 pi get cancelled, 4 1s are 4 2s are. So pi int is equals to 10 power minus 7 divided by 2 into I. So what is the inductance formula? Pi by I, right? So now if you take this I in denominator, then you will get pi in divided by I is equals to 10 power minus 7 divided by 2. So this is the value of inductance due to the internal flux. It is a never will be changed. It is constant for entire derivation. So మీరు ఏ ప్రాబ్లం ఏ టైప్ ఆఫ్ డెరివేషన్ చేయాలన్నా with respect to the inductance you have to use this equation, final equation. So what is the inductance due to the internal flux is 10 power minus 7 by 2 Henry per meter. So it is usable in your problems also. So just remember this, the final equation of inductance due to the internal flux is given by the 10 power minus 7 by 2. So sometimes what you will get, what they will ask me is when the 5 ampere current is flowing through the particular conductor, what is the internal flux linkage? They will ask like that. So at that time we have to use this formula. So pi internal flux linkage divided by I is equals to 10 power minus 1 by 2. So if you want to calculate this value, so directly multiply with I, then you can calculate that when the 5 ampere current is flow through the conductor, then this much of a flux linkage will be happening in the conductor. So this is about inductance of a conductor due to internal flux. So until now you have any doubts, just clarify that. సో ఇంతవరకు మీకు ఏమైనా డౌట్స్ ఉన్నాయా? సో ఇది డెరివేషన్ మీకు అర్థమైతే రిమైనింగ్ డెరివేషన్స్ అన్ని ఈజీగా అండర్స్టాండ్ చేసుకోవచ్చు. సో జస్ట్ సే దట్ there is any difficulty to understand in derivation part, whatever it may be, just say itself. సో అందరికి క్లియర్ అయింది కదా? సో క్లియర్ అని చెప్తే నెక్స్ట్ డెరివేషన్కి వెళ్తాం. ఆర్ యు క్లియర్ అప్ నౌ? Bhargav is there?
Yes sir.
అర్థమైంది ఎంతవరకు? Right. So next derivation is inductance of a conductor due to external flux. So this is the final equation for just note. So ఈ డెరివేషన్స్ చేసిన తర్వాత ప్రతి ఒక్క ఫార్ములా మీరు కీ పాయింట్స్ నోట్ చేసుకోండి. ఎందుకంటే మీకు ఏ ప్రాబ్లం చేసినా కానీ తక్కువ ఈ ఫార్ములాస్ గుర్తు రావాలి. సో ద ఇంటర్నల్ ఫ్లక్స్ ఇస్ ఆఫ్ కండక్టర్ ఈజ్ ఈక్వల్స్ టు 10 పవర్ మైనస్ 7 by 2. సో ఆ ఫార్ములా మీకు అయిపోవాలి, అంటే ఈజీగా రిమెంబర్ అయ్యాలి. సో అప్పుడు మీరు ఎటువంటి ప్రాబ్లం అయినా చేయగలుగుతారు. సో ఈ సబ్జెక్ట్ లో మీరు ప్రాబ్లం చేయాలంటే యూ షుడ్ హ్యావ్ టు నో ఆల్ ఫార్ములాస్ యూజింగ్ వాట్ యు ఆర్ డిస్కసింగ్ ఇన్ ద సబ్జెక్ట్. So then only you can solve the problem. Why? Because they won't ask the problem directly. So they are interlinked with each other. సో అప్పుడు ఏమవుతుందంటే మీరు ప్రతి ఒక్క ఫార్ములా తెలిస్తేనే అందులో ఉన్న ఇంటర్ పారామీటర్స్ బేస్, సపోజ్ ఇప్పుడు జస్ట్ ఇంటర్నల్ ఇండక్టెన్స్ అంటే మీకు 10 పవర్ మైనస్ 7 by 2 తెలిస్తే చాలదు. సో ద ఇండక్టెన్స్ కెన్ బి రిటన్ as ఇంటర్నల్ ఫ్లక్స్ లింకేజ్ డివైడ్ బై I రాస్తేనే దెన్ యూ కెన్ క్యాల్కులేట్ దట్ unknown parameter from this equation. So that's why I'm saying that each and every లైన్, సో డైరెక్ట్ గా వేస్తే మీకు అర్థం కాదు కాబట్టి ఈచ్ అండ్ ఎవ్రీ లైన్ మీకు స్టెప్ బై స్టెప్ వేసుకుంటూ వస్తున్నాను. సో జస్ట్ రిమెంబర్ దట్ ఎల్ ఈజ్, సో మనకు ప్రతి ఒక్క డెరివేషన్ అనేది ఈ ఫార్మాట్ లో తెచ్చుకోవాలి. ఎల్ ఈజ్ ఈక్వల్స్ టు పై సై బై ఐ. సో అది ఏ టైప్ డెరివేషన్ అయినా కానీ యూ షుడ్ హ్యావ్ టు బ్రింగ్ దిస్ ఈక్వేషన్ ఇన్ టర్మ్స్ ఆఫ్ ఎల్ ఈజ్ ఈక్వల్స్ టు సై బై ఐ. సో దెన్ ఓన్లీ ఇట్ ఈస్ కాల్డ్ యాజ్ ఇండక్టెన్స్. So until now we derived the derivation with respect to the internal flux linkage. Now we go for external flux. So this is the derivation we are going to derive, that inductance of a conductor due to external flux. Now let me tell, so this is the conductor here. So this is the normal conductor and we are calculating. So మన ఇంత ముందు ఓన్లీ ఇన్నర్ సర్ఫేస్ వరకు క్యాల్కులేట్ చేస్తాం. సపోజ్ ఏదో ఒక పాయింట్ దగ్గర, ఇప్పుడు మనము అవుటర్ సర్ఫేస్ యూజ్ చేయాలి. సో లెట్ బి కన్సిడర్ ఇట్ ఇస్ a conductor and when the flux will be generated in the center of the point, it will travels to the surface area. సో ఈ విధంగా ట్రావెల్ అవుతా వస్తుంది. సో ఈ విధంగా వచ్చిన తర్వాత మనకి ఎక్స్టర్నల్ ఫ్లక్స్ అనేది ఎలా ఉంటుంది, దానివల్ల దాని యొక్క ఇండక్టెన్స్ ఎలా చేంజ్ అవుతుందో మనం ఇక్కడ కనుక్కుంటాం. So until now we discussed that what is the flux linkage will be happening inside the conductor. Now we are going to derive that what is the flux linkage is happening outside the conductor. Now let me consider that here the figure shows that 2 points. One is, see here, this is there. I am considering 2 points. One is P1 and P2. This P1 is a point. It is the surface, outer surface of the conductor, and P2 is somewhere where somewhere in some far away distance between that outer surface of the conductor. So I'm taking that 2 points P1 and P2, and from the origin of the conductor, that is center point of the conductor, to the P1, I'm denoted as distance is D1. From origin to P2 is D2. So based on these 2 points, we can calculate that. So until now, we derived the equation up to here, from here origin to here. Now we are deriving that derivation from here to here. So this is called as inductance due to the internal flux. This is called as inductance due to the external flux. If we are adding these two, then we can find that total inductance of a conductor. Now, so all assumptions are assumed here. Now let me take any flux. So after flux linkage, if you take any one flux linkage, it is in the tubular form. Tubular means it is circular form, right? So if we take one of the flux linkage form, and from that form, that center point to that flux linkage, I'm denoting as a distance is x, and the change in distance between that two successive flux linkage is denoted by the dx. And here also I'm considering that hx is constant. Why? Because the current to the entire conductor is constant, then only it will generate the constant flux. So what we derived in the previous derivation, the same thing will be happening here due to some differences. Let me see what are the difference we are going to derive here. Right. So already this is the equation we obtained from the Ampere's law. So how we can obtain means, see already integral of h ds is equals to I. So here integral of ds can be written as 2 pi x. So by using these two equations, directly I can write as 2 pi x hx is equals to I, and hx is equals to I by 2 pi. So why I am considering hx means, suppose here, so I'm taking the distance. So distance point is, so this is the flux linkage I'm considering here, right? So this is the part I'm considering here from center to this point x, right? So that's why I'm considering here x is the distance between the center point to what we consider as a flux linkages. So that's why I'm denoting all parameters in terms of hx, right? So from this equation, you can write that hx is equals to I by 2 pi x. So already we obtained in previous equation. From this equation, already we know the relation between flux density and flux intensity. So bx, so substitute hx here, then you will get bx is equals to nu I divided by 2 pi x Weber per meter square. So, and I think you guys well are known about until this equation. So why? Because the same equations what we derived in the previous derivation, right? So this is the change in flux with respect to the area. D pi is equals to flux density into dx into L. So here L, I'm considering L as a 1 meter, and d pi can be written as, substitute bx here, then you will get nu I divided by 2 pi x into dx. Now finally d psi can be written as pi I. So here the flux linkage d psi per meter are equal to d pi. So this is in outer surface, that is the outside of the conductor, the change in flux and flux linkage both are equal to each other. So that is the difference in previous derivation and this derivation. So d psi is equals to substitute d pi here. So this is referent equation 5. Now the total flux linkage between P1 and P2. So here I am considering the 2 points. So this is the conductor and this is the outer surface. That is the this is the away from the surface. So I'm considering 2 points. One is surface of that is P1 and P2. So now we have to find that what is the flux linkage between these 2 points, and the flux linkage will be changed with respect to the distance from D1 to D2. So D1 is the distance from origin to the point P1, and D2 is the distance from origin to point P2. And by using this equation, we can see here pi12 is the flux linkage of due to the current with respect to C2 అంటే outer surface అంటాం, అందుకని flux linkage pi12 అంటాం. So this is the flux linkage will be changed from the D1 to D2, and this is the equation of flux linkage already we derived last derivation. And pi, so here except 1 by x remaining all terms we have to bring the outside of the integration and 1 by x. So here 1 by x can be written as integration of 1 by x is ln x, and if you substitute the limits you will get ln d1 d2 minus ln d1. So if in logarithmic there is a minus, means you have to, how we can eliminate, by bring this in division manner. If it is plus, what you will get ln into d1 d2. So if it is plus you have to multiply, if it is minus you have to divisible, right? So after integration of this 1 by x you will get lx ln x, that is log x. Log x limits, upper limits d2 and d1. If you substitute here ln d2 minus ln d1. So based on the logarithmic equations I can make this equation to the ln d2 by d1. So pi12 is equals to I nu I by 2 pi ln d2 by d1. So already we know that the value of nu is equals to nu naught into nu r. So here nu naught is the permeability of the free space, 4 pi into 10 power minus. So this is the important question. So meeku ఇది ఈ క్వశ్చన్ లో అడుగుతాను, వాట్ ఈస్ ద వాల్యూ ఆఫ్ పర్మియబిలిటీ ఆఫ్ ఎ ఫ్రీ స్పేస్? So 4 pi into 10 power minus 7 and nu r is equals to 1. So this is the permeability of a non-magnetic material. And if you substitute these two values here, then finally you will get pi12 is equals to 2 into 10 power minus 7 into I into ln d2 by d1. So how we can find the, how we can obtain inductance? So let's bring I to the denominator. So psi by I equals to 2 into 10 power minus 7 ln d2 by d1. So this is the equation for the flux, that is external inductance of a conductor due to the external flux. So first is ఏమొచ్చింది 10 power minus 7 by 2. So this is the inductance of a conductor due to the internal flux. Second ఏమొచ్చింది inductance to the external flux is 2 into 10 power minus 7 ln d2 by d1. Now by adding these two we can find that total flux, total inductance of a conductor due to that addition of internal flux and external flux. So until now we separately derived about internal flux as well as external flux. Now when we combine these two, then we can find that total inductance of a conductor. See here, so this is the derivation for obtaining the total flux linkage. How it means, suppose I will tell you that this is the conductor. From origin to surface I am taking the radius r. So this is the point r. Now if you want to measure the inductance, so after flowing the current the flux will be generated like this. So after that the flux will be flowed outer surface of the air to the up to some distance. So we don't know distance, that distance we can say that infinity. So it means that out of conductor the flux linkage will be travel from point r to infinity. So we have to derive the derivation for the total flux linkage from r to infinity. So r is the outer point of the conductor and infinity is some point where the flux will be going to travel here. Now so here nu I divided by 2 pi x into dx. Instead of nu I can write nu naught into nu r. So already nu r is equals to 1, right? So there is no need to write that here. And overall flux linkage is given by, so total flux linkage is equals to internal flux linkage plus external flux linkages. So let me see how will come when we add these two flux linkages. Right, so this is the total flux linkages. So here I am not substituting 4 pi into 2 power 10 power minus 7 here, just I am writing nu naught as it is, nu naught into I divided by 8 pi plus integration of r to infinity and nu naught I divided by 2 pi x dx. So from this equation nu naught I by 2 pi take common, into 1/4 plus integral of r to infinity I divided by x into dx. So this is the total flux linkage of a conductor. Right. So this is about calculation of inductance of a conductor due to internal flux and external flux. If you understand these two equations, that is internal flux is given by 10 power minus 7 by 2 and inductance due to external flux is 2 into 10 power minus 7 ln d2 by d1. సో ఈ రెండు ఫార్ములాస్ మీరు కనుక నేర్చుకుంటే రిమైనింగ్ అప్కమింగ్ డెరివేషన్స్ అన్ని ఈజీగా చేసేయచ్చు. సో దట్ ఈజ్ ఇట్. అండ్ వన్ మోర్ థింగ్ ఇంపార్టెంట్ ఫ్రమ్ దిస్ టాపిక్, సో దట్ ఈస్ ద డెరివేషన్ విచ్ ఇస్ రిలేటెడ్ టు ద ఇండక్టెన్స్. డెఫినెట్లీ వన్ క్వశ్చన్ యూ విల్ గెట్ ఇన్ ఎక్స్టర్నల్ ఎగ్జామ్. ఓకేనా? సో అందుకని జాగ్రత్తగా ప్రాక్టీస్ చేసుకోండి. సో ఆల్రెడీ ఈ డెరివేషన్స్ అన్ని మీరు నోట్ చేసుకున్నా చేయకపోయినా కానీ మీకు ఆల్రెడీ మెటీరియల్ సెండ్ చేస్తాను. సో ఆ మెటీరియల్ లో ఉంది. సో ఏ రోజు క్లాస్ ఆ రోజు నోట్ చేసుకున్నట్టే then you can remember the how to derive the a particular value. సో ఆ విధంగా చేసుకోండి. సో దీని తర్వాత different inductance calculation we are going to derive, that is for single phase two wire system, three phase system, symmetrical spacing, unsymmetrical spacing, transposed, untransposed. సో ఈ విధంగా మనకు 5-6 డెరివేషన్స్ ఉన్నాయి. ఇట్ డిపెండ్స్ ఆన్ ద ఇండక్టెన్స్. సో 5-6 డెరివేషన్స్ మీకు అర్థం అవ్వాలంటే ఫస్ట్ మీకు ఈ రెండు ఇంటర్నల్ ఫ్లక్స్ ఎక్స్టర్నల్ ఫ్లక్స్ లింక్ అర్థం అవ్వాలి. సో దెన్ ఓన్లీ యూ కెన్ అండర్స్టాండ్ దట్ రిమైనింగ్ 5 or 6 డెరివేషన్స్. సో మీకు ఎటువంటి అంటే ఈజీగా అర్థమయ్యే విధంగా చెప్తాను. సో మీరేం చేయాలంటే మీకు ఎక్కడన్నా ఏ డౌట్ వచ్చినా కానీ ఆ క్లాస్ లోనే క్లారిఫై చేసుకోండి. ఎందుకంటే క్లాస్ సో ఇట్ ఈస్ నాట్ ఏ థియరీ సబ్జెక్ట్. So if it is theory means you can study your own yourself, but it is a completely derivative problem and subject. You should have to guidance from others. So that's why I'm saying again, you should have to practice more and more, and you should remember the all equations what we discussed in the class itself. So okay students, until now you have any doubts? Sushma is there?
Good afternoon, sir.
What is the units of magnetic field intensity, ma?
Magnetic field intensity, na sir? Weber per meter, sir.
కాదమ్మా, వెబర్ పర్ మీటర్ స్క్వేర్ అనేది ఫ్లక్స్ డెన్సిటీకి, మ్యాగ్నెటిక్ ఫీల్డ్ ఫ్లక్స్ డెన్సిటీకి. నేను అడిగేది మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీకి. కిరణ్, మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ దట్ ఈస్ హెచ్. కిరణ్, వాట్ ఈస్ ద యూనిట్స్ ఆఫ్ మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ? Jayaswari, Sindhu, what is the units of magnetic field intensity?
Tesla, sir.
అది మ్యాగ్నెటిక్ ఫీల్డ్ ఫ్లక్స్ డెన్సిటీ కమ్మా, నేను అడిగేది ఇంటెన్సిటీ హెచ్. సో కన్ఫ్యూజ్ అవుతుంది. హెచ్ ఈస్ నథింగ్ బట్ ఏ మ్యాగ్నెటిక్ ఫీల్డ్ ఇంటెన్సిటీ. B is a magnetic flux density and the relation is B is equals to nu x. The units of magnetic field intensity is ampere ton per meter, AT ampere ton per meter, and the units of magnetic flux density is Weber per meter square, and it is also has Tesla. So ఈ యూనిట్స్ బాగా గుర్తు పెట్టుకోండి. ఓకేనా? ఇంటెన్సిటీకి వచ్చి ampere ton per meter and flux density వచ్చేసి Weber per meter square or Tesla. సో ఈ క్వశ్చన్స్ మీకు స్ట్రిప్ టెస్ట్ అడుగుతాను. సో అందుకని మీకు జస్ట్ రివైజ్ చేస్తాను. So don't confuse that. Intensity is different and flux density is different. Right. So అందరికి క్లారిటీ వచ్చింది అమ్మ డెరివేషన్ పైన. సో ఇంకేమైనా డౌట్స్ ఉన్నాయా? Do you have any doubts up to now? సో మీకు క్లియర్ అయిందంటే క్లాస్ ఎంజాయ్ చేస్తాం. రైట్. సో ఐఎమ్ గోయింగ్ టు సో నెక్స్ట్ క్లాస్ వచ్చేసి హౌ వీ కెన్ క్యాల్కులేట్ ద ఇండక్టెన్స్ ఫర్ సింగిల్ ఫేస్ లైన్. ఓకేనా? సో ఈ డెరివేషన్ మీరు ఒకసారి బాగా క్లారిటీగా చూసుకోరండి. నెక్స్ట్ క్లాస్ వచ్చేసి హౌ వీ కెన్ క్యాల్కులేట్ దట్ ఇండక్టెన్స్ ఫర్ ఏ సింగిల్ ఫేస్ లైన్. సో సింగిల్ ఫేస్ లైన్ లో ఇండక్టెన్స్ అనేది ఎలా క్యాల్కులేట్. సో ఇప్పుడు మనం ఇంతవరకు మనం ఒక కండక్టర్ కి యూజ్ చేస్తాం. ఇప్పుడు మన సింగిల్ ఫేస్ లాంటి 2 కండక్టర్ వస్తాయి, ఒకటి ఫేస్ ఒక న్యూట్రల్. సో ఆ లైన్స్ లో మనం ఎలా క్యాలిక్యులేట్ చేస్తామో అది రేపు క్లాస్ లో చెప్తాం. ఓకేనా? సో జస్ట్ ఒకసారి చూసుకొని రండి, రేపు క్లాస్ మీకు ఈజీగా అర్థమవుతుంది. థ్యాంక్ యూ. ఐఎమ్ గోయింగ్ టు ఎండ్ ద క్లాస్. థ్యాంక్ యూ.